Physics. So here we go. I'll start with an overview of hadronic physics in Geant4 and basically give you an idea of how it's put together and the theory behind it. And then I'll talk about some specific models which go in physics lists, pre-compound and de-excitation models, and finish with cascade models. And then the following two, the other two hadronic talks today will deal with some of the other models that are available. So we talk about radioactive decay and neutron physics and all of that. So as you already know, so this is kind of a review, hadronic processes, models, and cross-sections follow the same structure or framework as the electromagnetic, more or less. There are some differences. But Geant4 physics is assigned to a particle through a process. So all the physics happens in the process. You assign the process to the particle. And each process can be implemented in one of two ways. You can write a class that has all the information, all the physics in it, in just one class, or you can take advantage of the Geant4 structure and write a model. So that way you can have the same process, doing the same kind of physics, but in different ways. So if you like a model that does some kind of physics better, you can write one and substitute it in a modular way. So this is very good. We do strive in Geant4 to provide alternatives. So most of the cases, there are at least two models for every process, and in many cases, there are more. You also have to assign cross-sections. So as Mihaly told you yesterday, you need a cross-section to get the interaction length. And then once you're at the point of interaction, you need some code to tell the track what to do. And so lots of options for cross-sections as well. And here's how it looks as kind of a block chart. So you have a particle, and to this particle you can assign any number, well, almost any number, a very large number of processes if you like. It could be an at-rest process, in-flight, what have you. And then each of these processes can be made up of a number of models. So you could have very many models representing a particular process, and then, of course, the models correspond to cross-sections. And you can have a lot of these. And these, I'll tell you how these are put together. So before I go any further, let me make a general comment about hadronic physics. With the electromagnetic case, you have a track that's going along, and you know from the interaction point where that's going to happen. And it's essentially a point interaction. And so at that point, you take the Z and the A of the atom that it's interacting with, you do a calculation of the final state particles, and you're done. You put it out. I mean, it can be complicated, but it's a little different in hadronic physics because in many cases you have the hadron coming along. It interacts according to the cross-section. And now you are in a situation where you have a hadron at a nucleus, and you have to have a very detailed model of the nucleus. So it is some kind of sphere with a Wood-Saxon density, so the density is high in the center, and then it falls off at the edge, and you have this tail. And so that is the nuclear potential. So once the hadron enters the nucleus, you start another Monte Carlo. So now you have this track inside the nucleus, which is bouncing around in the nuclear potential and interacting with many particles within the nucleus in order to produce the final state. So it's more complicated, and there are more calculations. And because of this, hadronic interactions typically are maybe 8 or 10 times slower than electromagnetic. There are just many more calculations because you're doing a Monte Carlo within a Monte Carlo to get the final state. And part of this is the reason for part of this is that there's no single theory that handles all of the hadronic physics that we can do. For electromagnetics, we have quantum electrodynamics. It's nice and beautiful. For very high energy hadronic physics, we have quantum chromodynamics. So if it's TeV physics, we know very well what to do, and that's fine. And very low for nuclear energy, we have some very nice theories for nuclear physics. But in between, few GeV region, it's very messy. So we have to have, generally speaking, several models and several cross-sections to cover the entire energy range that you might want in a physics list. And that's why hadronic physics tends to be a little more messy. So let's go to the cross-sections. Each of the processes we provide has a default cross-section. So if you do nothing, you'll get a cross-section. Don't worry about it. And For these, we basically divide up the hadronic processes into fission, capture, elastic, and inelastic. And each of these can be overridden by another cross-section set if you like. It's your option. And there are different types of cross-section sets. So some of them are relatively simple. It's just a few numbers that represent the nuclear shape, for example. Others can represent large databases. For the neutrons, high-precision neutrons, we have the NDEF database, which is quite large. And for every particular interaction, it needs to be looked up. And some are all just equation-driven, and we don't have a lot of data, so we have to rely on the theory. So some of the alternative cross-sections that we have are the low-energy neutrons, and I mentioned this. G4NDL is based on the NDEF distribution. The Livermore database is also available. And if you like to do very low energy, like thermal neutrons, we have those cross-sections. Proton and neutron reaction cross-sections, generally you're taking from phase shift experimental information. And so we have cross-sections there. And then we can do ion-ion or ion-nucleus collisions. And for these, we have Tripathi, Shen, and Cox cross-sections. And these are good for medium to low energy, so below 10 GeV per nucleon. And then we have a lot of pion reaction cross-sections. So all of these are available to go in place of the ones that we already offer. So I mentioned that we probably need more than one cross-section for any particular model or any particular process over a period, over a range of energy. And so how does Geant4 decide when to go from one cross-section set to the other? Well, it's all dependent on the energy. So on this axis, we have the energy of the incident particle. And as I said, if you do nothing, you get a cross-section set which is applicable for all energies. So fine, you do nothing, you get something. However, when you start putting in your own, let's say that you write a cross-section set or choose one of the alternatives, that could be set 1, and it covers this energy to this energy. And you may have set 2, which covers this energy to this energy. And then so on and so forth. So what happens is that, well, the energy of my particle is indicated by this pointer, and it takes the last cross-section set that is loaded in. So in this case, it will see set 3 from this energy to this energy. If the energy is lower, then it will see set 1. If it's higher, it'll see set 4, and then it'll go back here to set 2. So the stuff that is underneath is invisible. Just one overloads or overrides the one on top. So now to models. We have models which are driven by lots of data. So these are essentially the stupid models. All they do is look up a table and give you an answer. So for lots of low energy cases, we have this. It's already tabulated from experiment. We have cross-sections, angular distributions, and multiplicity. And it just does a lookup table. So that's very nice. It tends to give you the best results. For interaction length and final state, the models have to do some interpolation of the cross-sections. So you're going to have to interpolate not only the cross-section, but also the angular distribution. And this can be a combination of Legendre coefficients in cosine theta. Examples of these would be the neutron models. So the high-precision neutron models apply below 20 MeV. Coherent elastic scattering, so this is for proton-proton, neutron-proton, and neutron-neutron scattering, and radioactive decay. I'll talk about that this afternoon, but it is also dependent on a large database for its information. Now, the theory-driven ones, these tend to be a little bit nicer because they operate at, generally speaking, higher energies. So this is the quantum chromodynamics models. It could be Glauber theory for nucleus-nucleus interactions, or exciton theory for the lower part, that is the nuclear physics. And here the final states are calculated by some theoretical calculation. So we like this model because it's very predictive. We don't have as many knobs to turn to tune it. So what we get, we tend to believe, at least if we believe the theory, then we believe what this model predicts. So that's nice. And the examples of this model are the quark gluon string models. So this is the FTF model and the QGS model that I'll talk about. The intranuclear cascade, so that is basically a model that applies at intermediate energies, let's say below 20 GeV and above a few hundred MeV. And then the nuclear de-excitation and breakup models. This is used a lot for medical physics and space applications. Here is a partial inventory of all of the hadronic models in Geant4. And it just gives you an idea of the particle types and the energies for which these models apply. So at the x-axis here, we have, roughly speaking, a logarithmic scale of energy for the incident particle. And then you see by the colored bar the model and the energy range over which it applies. So let's start down here at the bottom. These yellow bars represent the cascade models. So they are applicable down to fairly low energy and up to roughly 10 GeV. And we have the Bertini cascade, the binary cascade, and the INCL++ cascade. These match up pretty well. So because these models are not applicable above higher energies, we now have to go to some of the string models to handle the very high energies. And they overlap a little bit, so that's good. So we have the Fridtjof string or FTF model and the QGS model. And in a physics list, we usually put one of these with one of these to cover the entire energy. Now, once we use the cascades, we have to de-excite the nucleus, and I'll talk about that. So we have pre-compound models and the lower energy models which produce fragments when the nucleus breaks up. The QMD and Wilson abrasion are the nucleus-nucleus models. So instead of a simple pion or a proton coming into a nucleus, you have a carbon atom or carbon ion coming into a target of lead or what have you. And then the precision models, this is the high precision neutrons. This is also a neutron model. And at the very low energy, we have the radioactive decay and the absorption at rest. So here you can have a mu minus or a pi minus or a k minus or antiprotons. They come to rest, they get absorbed, and you have to calculate some interaction in order to produce the final state after that interaction. And then finally, we have the photonuclear and electronuclear. So what happens when you have a gamma or an electron or a muon colliding with a nucleus? We have to provide the electronuclear interactions there as well. So we talked about cross-sections, needing several of those. We also need several models to cover the entire energy range. It's similar, but a little bit different than the cross-sections. So once again, we have the energy on this axis. And we have the models. So let's say we have 4 models defined in our physics list. And model 1 covers this energy range, model 3 this energy range, model 2 and model 4. So how this works is, once again, we have an energy pointer based on the incident energy of the particle. And if it's here, it gets this model. If it's here, well, I'll tell you about that a little later. If it's here, it gets purely this model. But what about the overlap? Okay, we do this on purpose in order to get a smooth behavior when transitioning from one model to the next. So let's suppose we have a cascade model at low energy and a string model at high energy. We want to be sure that the angular distributions and the energies of the final state particles merge smoothly from one model to the other. So what we do is, if the energy is in this overlap range, we choose a random number. And if the random number is low, then it's near the edge of model 3, and it's about 100% model 1 and 0% model 3. At the upper edge, it's 100% model 3 and 0% model 1. So it's just a linear ramping based on a random number, and that's how we blend the two models. So if you look deeply into a physics list, you'll see one model that has an energy range this and another module that an energy range that, and they overlap. That's the reason why they overlap. Now, here we have a problem. If the energy falls here, you're going to get an error. Okay, the physics list that Geant4 provides, this error doesn't happen, but if you write your own, you may forget that, oh, this model doesn't go higher than this energy, and this model doesn't go lower than this energy. So you have a problem. Models have to go over the entire energy range. And unlike the cross sections, we do not have default models. So you always have to provide a model. Here's another error. So you cannot have a situation in which one model is entirely overlapped by another. The code doesn't know what to do, so it throws an error. So that's the model and cross-section management, the kind of technical aspect of the code. And here is a cartoon of what happens at all energies in Geant4 hadronics, just to give you an idea qualitatively about what's happening with the physics. So let's start at the very high energies and say we have a 1 TeV hadron coming into a nucleus. And so it is incident upon the nucleus, and it will find 1 or 2 nucleons within the nucleus to interact with. And so it does so using a string model, which I'll talk about later, and then exits the nucleus, and some final state particles are produced. And this is interesting because at high energies, this interaction is so boosted forward that the interaction and the final states of that interaction are still quantum mechanically coupled very tightly for a long distance. So you could have a pion interacting with a nucleon in the nucleus, producing final state particles, but they're still tightly coupled. And so they will not actually produce final state hadrons until they're well outside the nucleus. So this is a very interesting aspect of high energy interactions. So this interaction happens, you get some hadrons produced outside the nucleus, but you're left with lots of energy deposited in the nucleus from the particle passing through. So now, this has already happened. Let's go to the next stage, and now we've gone down in energy to between 100 MeV to a few GeV. So this is the track of the original particle, and it's left some energy and disturbed some of the nucleons within the nucleus. And so what do? They propagate through the nucleus, and they can bounce off the edges and do things like that, but they also strike other nucleons, and they produce other nucleons, and you have a cascade or a kind of a chain reaction within the nucleus. So this is the cascade phase. This is a very time-consuming process, but it produces all these secondaries in the nucleus, and some of them get reabsorbed in the nucleus. Some of them escape. So when they escape, they get put into the final particle stack in Geant4. Now, after this phase, we have either absorbed all these medium energy particles or they have escaped. Now the nucleus is in this state. So this is called the pre-compound state, and I just put some holes in here to make it look like it's a messy, disturbed nucleus, which it is, but it still has some energy to get rid of. And so what happens in this case, these particle hole states that are created by the cascade stage have to collapse in order to go down to a lower energy state. And when they do so, they emit protons and deuterons and tritons and alphas, so that the nucleus then de-excites to a lower state. And this is where you get multifragmentation and lots of the other nuclear physics processes. Finally, after that's happened, now we're down to a fairly low energy nucleus, between 10 MeV down to, let's say, thermal neutron energies. And now all we have is the so-called evaporation models, where we send off gammas and neutrons and nothing else. So this takes us down to zero energy. So we have models that cover every stage of this process. So let's start now at the lower energy part, and we'll talk about the pre-compounds. So this, remember, is this stage. So we have nucleon-nucleus interactions that are happening, and generally this model is valid between 0 and about 170 MeV for protons and neutrons. This is used a lot for medical applications. So you take a nucleus, which is a highly excited set of particle hole states, and they collapse, and when they do, they emit all of these particles, possibly emit all of these particles, down to nuclear equilibrium. Once you reach that state, there are 4 ways in which the nucleus can be de-excited, and I'll talk about those. There are 2 cascade models that have these models embedded. So the Bertini cascade has a pre-compound model, and there is another model, which is a Geant4 native model, which uses that. So what happens when you try to de-excite a very messy excited nucleus? Several things can happen. If it's a fairly light nucleus, let's say A is less than 17, then the nucleus can entirely break up until you have nothing left. So you could have just alphas and tritons and things like that, and it just explodes. You could have photon evaporation, or you could have multifragmentation. So this is something for the medium-sized nuclei in which you could produce lithium-7 fragments or beryllium-8 fragments or things like that. And then for the really heavy ones, fission will de-excite the nucleus. In the case of the de-excitation models, we assign these directly to a pre-compound model and then directly to a process. So you usually, as a user, you don't change these. If you become an expert user and you say, I would like a different multi-fragmentation model, you can put that in. But for the most part, people do not bother with this because it's pretty well understood and people seem to be happy with it. So we call these submodels, and we tend not to change them very much. So in more detail, these are the de-excitation models. So the Fermi breakup, as I said, is good for A less than 17, and it only produces these small particles as a final state. Fission is good for A greater than 65. And multifragmentation is a statistical breakup model. So you propagate these fragments in the nucleus within the Coulomb field, and then the alphas or the tritons or the lithium-7s are emitted over the Coulomb barrier of the nucleus. And this is good for energies of about 3 MeV per nucleon. Photon evaporation, this is important, especially if you're doing anything with gamma radiation, radioactive decay, and things like that. This is usually the final stage of nuclear de-excitation. So the nucleus is left in a high state. It can emit a gamma and go to a lower state without changing its Z or its A. And all of these gamma lines, all of the nuclear structure plots, if you've ever looked at those, some of them can be like a forest. They are all included in the ENSDF database. So what this model does, it says, I have a nucleus in this excited state. Look up in the table, what is the probability that I go to the ground state? Or what is the probability I go to an excited state and then have a chain decay? So all of this is there, and for this you need to download a data file, and you've probably already done this in the hands-on, I believe. So it deals with gamma levels for about 2,100 nucleids, and it handles all the gamma cascades and electron emission and so on and so forth. Now, if you start to write your own physics list, here is how you would put the pre-compound model into it. So you have to define something called a G4 excitation handler. And excitation handler is where you put all the breakup models or the multifragmentation models. Once you've instantiated this, so now you have this pointer handler, you give that to the pre-compound model so that the pre-compound model knows how to break up the nucleus. Now we have this model. We go ahead and define an inelastic interaction for a neutron. So this class is called G4 neutron inelastic process. We construct that, get its pointer. And now we say register me. So we register this model, pre-compound, to the neutron. And we give the neutron process to the neutron manager. And now the neutron knows how to decay, or how to cause a pre-compound interaction with nuclear breakup. So here we have done this in isolation. Usually it's put in combination with a high energy or a cascade model. So if we start with a FTF or a Fridtjof string model, and then after that high energy interaction we want to de-excite the nucleus, we need a pre-compound model. And so if you see a nucleus FTFP, that means it's the FTF string model followed by the pre-compound de-excitation. And so this in the code is actually being called. Questions about anything so far before we go on to the cascade models?
You have an incident one, right? So the primary one. So you have the first hadronic interaction. Then it produces secondary particles.
Mm-hmm.
Then these secondary particles, they will follow the same path as the primary particle. If it goes and in your detector and create secondary hadronic interaction, we follow the same way as the primary particle?
No. So let's say that you have a primary particle, a proton, goes into a gold nucleus and produces, through the pre-compound model, let's say, protons and neutrons and alphas. Each of those particles has a different process, and so they will be propagated as a separate track to the next nucleus. And so now you will have a proton inelastic process or an alpha inelastic process. And then they can do whatever they like depending on what models you have assigned to them.
Okay, so maybe I have made that my question. So once you have this secondary alpha, for example, then it will go through as if it was a particle on its own.
That's right.
Following the same models that you have reassigned before your...
Yes, yes.
According to its own energy.
According to its own energy and the models that you have assigned to it. Yes. Yes.
The break-even model from binary cascade 13 models are different.
Yes.
And each energy, the break-even model starts with cascade model.
The cascade models generally, Bertini is probably good from 15 GeV down to 0. And the INCL is probably good from 10 or 12 GeV down to 0. Each of them have their own pre-compound models embedded.
But this pre-compound starts with the same energy or...
Pre-compound can be used as a separate model, and so that starts at, let's say, about 170 MeV for the incident particle and goes down to 0. If you use a binary cascade model, then the binary cascade goes from the binary cascade to the pre-compound model that I talked about. And that transition happens between 100 and 200 MeV.
It's possible to use the same pre-compound model using the Bertini and binary cascade?
Yes, there is an interface to use that pre-compound in the binary in the Bertini cascade as well, if you like it better. Mm-hmm. Cascade model. So this is the one where I told you where you have a particle going in the nucleus, it hits other nucleons in the nucleus, and then they bounce around in the nuclear potential and have other collisions and make a mess. So this is what we do. The energy range here is inconvenient, as I said. It's too high to be real nuclear physics model. It's too low to be a good QCD model. So we have to do all of this stuff. This probably goes back to some of the earliest Monte Carlo codes because this is the energies that they were dealing with. And it's a very time-consuming model. Some of these cascade models are faster than others. And an interesting thing is that if you're used to nuclear physics, then you're used to a model saying, if I have a reaction like protons on nitrogen-14 produces oxygen-14 and a neutron, then you know what the yield of that reaction should be. And people say, why doesn't this happen when I use a cascade model? That's because the cascade models don't have that detail of nuclear structure. So if you're using a true nuclear physics model, you have the shell model, and you know what these states are supposed to do. But those states are not explicitly included in the cascade. It's a much more average model. You will get this reaction, but you will not necessarily get the predicted final state rate. So just a word of warning in case you run into that. So let's start with the Bertini cascade. It is a so-called classical cascade, so it's not really quantum mechanical. We just treat these things as if they're billiard balls bouncing around in a potential. So there's no scattering matrix. As I said earlier, this can be traced back to some of the earliest codes. I think the origin of Bertini goes back to 1968. So really primitive days of computing. The core code is based on the fact that all of the interactions within the nucleus are assumed to occur as if they were in free space. So you have a pion coming in and it encounters a neutron in the nucleus. We would just say, or a proton. We would just say that is just like the reaction of a pion hitting a proton in free space. Now we know that's not true because it's embedded in nuclear matter. So you have to make some corrections. So it's not the free space cross-section, but we take into account the Pauli exclusion principle and the nuclear density, and we make corrections after the fact. But for this, we have to tabulate all the free space cross-sections to do it. Once that process is done, then it transfers to a pre-equilibrium and equilibrium decay. It's a very simple pre-compound model in Bertini, and because of that, it's faster than the other pre-compound that I just talked about. But it's sufficient for most cases. So the target nucleus is somewhat crude. It's built of concentric nuclear shells, and so it has this kind of, instead of this nice, smooth Wood-Saxon shape, it has a step-like structure for the edge of the nucleus. It just saves time to do that. So this is what Bertini does. It's a lot like the first plot that I showed you, except that there's no high-energy part. So we have the incident particle coming into the nucleus, and then it produces secondaries, and those secondaries hit other protons and neutrons and produce pions and kaons and what have you. And then it goes through the pre-compound stage and then the evaporation stage. Bertini cascade is very good because it operates for everything. So every hadron, which is reasonably long-lived, is treated by this model. So you can even shoot in an omega minus and get an interaction out. It's valid for a fairly wide energy range. The original Bertini was usually only valid up to about 3 GeV, but we extended the range of this model so that it would overlap with the quark string models so that we could have a continuous coverage of hadronic models for the high energy experiments. This can also be used for gammas. So how would you put this in your physics list? Pretty easy because it's valid for almost all particles. Just instantiate it. Here the name is not so clear, but you just have to construct this class G4 Cascade interface and call the pointer BERT. Now that you have the model pointer, go ahead and create the inelastic process for a proton or a neutron or what have you, and register the model cascade interface to the process, and then add the process to the proton manager, and then you will have Bertini cascade. Here's an example of what happens when you have 730 MeV protons on carbon, and each of these plots represents a different angle range for the outcoming pion. So here we're looking at pi plus. And the triangles represent some data in each angular bin, or each energy bin at a given angle. And the curve represents what the Bertini cascade does to predict that. And so in most cases, we're doing all right. The shape is nicely reproduced. One warning when you're looking at validation plots, especially for hadronic physics, is that we almost always use log scales for the y-axis. So that means you can have factors of 2 difference here, and it doesn't look so bad. But if you put it on a linear plot, and that's because the models, as I say, are not perfect. And we sometimes have some large differences. So an alternative to this is the binary cascade. This is a much more detailed model. Much more detailed model. As a result, it's about 8 times slower than the Bertini cascade. But because of the increased detail, medical physics likes to use this one instead of Bertini. So the modeling sequence is very similar to the diagram that I showed. It's a time-dependent model, and it is more physical too, because when a particle comes in, like a pion, and it hits a proton, it forms a delta resonance. And then the delta resonance decays into several other particles. So this is actually the proper way to do it. It just takes more time. And the particles, when they're bouncing around in the nuclear potential, they follow curved tracks because the potential is spherical and it's just as if you were, for example, doing a particle in a Coulomb field. It would form an orbit. In Bertini, these are straight tracks, and so that's just another approximation. But this spends more time tracking curved trajectories within the nucleus. So it is not used for as many particles, but only for protons, neutrons, and pions. And the energy range for protons goes up to about 10 GeV. For pions, you shouldn't go really above 1.3 GeV. But for medical physics, this is perfect. A variant of this model is for light-ion reactions. So it's just an extension of the model, and you can send in carbon ions or lighter as projectiles. And I won't spend too much more time on this. It's basically the same thing as I said before. If you want to put this in a physics list, so you create the model, give the pointer of the model to the process, and then assign the process to the particle. And it's a little bit different if you're doing ion-ion reactions. In this case, you would instantiate the binary light-ion reaction and create something called G4 ion inelastic process. So this is collisions for all ions, and then give the pointer of the model to the ion process. And then instead of a specific ion, you have to do something called generic ion manager. So this is all of the ions, so carbon-12, lead-2, or well, not lead in this case, beryllium-8 or something like that. They're all encompassed in this ion manager. And so you would give this model to the ion manager. So the Bertini cascade, here's a validation plot for that. And each of these curves is, beryllium, aluminum, iron, and lead. And there are the various scaling factors so they can all fit on the same plot. And this is a plot of the cross-section, differential cross-section versus the incident energy of the particle. So this is 256 MeV protons in the spallation range. And we're looking at neutrons coming out at 7.5 degrees. So once again, it's a pretty good shape reproduction, but there are some differences. INCL cascade is a relatively new addition to Geant4. And INCL is a well-known Fortran model, which was converted by some of our collaborators into C++. And so that means it's allowed to be used in Geant4. So the model, this is also quite a sophisticated model, and therefore more time-consuming, but it's very good. And so some of the same model elements as the binary cascade. It's valid for more particle types. Actually, they have just extended this to kaons as well. So it's even more versatile than it was before. But it can also do incident ions. Bertini cannot do ions, but binary cascade and this model can do ions. And it's used pretty successfully in spallation studies. Here's an example. So the reaction here is protons on lead-208. And now we're looking at the mass number of the nuclear fragments produced by that interaction. So here is, these are the data points in black. And these are just two representations of how you use the INCL model. The green one, obviously, is the one we want. This is INCL, and it uses its own de-excitation model called ABLA. And there's a nice reproduction there. This other curve that doesn't work quite so well tries to use the Geant4 excitation handler, and so we know that that's probably not the best option. But this option is very good, and that is what you get when you use INCL. That's it for this part. So we talked about cross-sections and models and how they fit together in Geant4 hadronics, and the many options that you have for choosing this for your physics list. The hadronic framework makes it fairly easy for you to add more. So if you don't like something you have, there are ways in which you can write ones that fit the right interface for Geant4 hadronics. We have hadronic models which cover the pre-compound energy range. So this covers the low-energy projectiles and nuclear de-excitation. And we have 3 intranuclear cascade models that are good for intermediate energies: Bertini, binary, and INCL. That's it. Questions? Okay.
Oops, my privacy. Okay, it goes. Okay, this morning. So every time I show up, you have to switch your mind from physics to something else. I'm still supposed to be a physicist, but we'll see. So this particular talk gives you additional information of how you use our graphical user interfaces. But in this case, it tells you how you define your own UI command. Because once you create your own application built on top of Geant4, you definitely need to define some UI command so that not only yourself, but also users of your application should control the program, right? Through the UI command. So let me tell you how, first of all, how the UI works. And then I'll tell you how the basic UI command could be defined. Then followed by a bit more complicated command with a bit more complicated procedures. And UI generic messenger is a bypass, but I do not recommend much of use. And just a small comment on how you use it in multi-threaded mode. So basically, the scenario is the following. There are messenger classes in messengers in Geant4. Messenger takes several, not only one, but several UI commands. Okay, and each command may take whatever the necessary number of parameters that you have already tried. And when the messenger registers all the commands to the UI manager. Then a user types in the command or whatever. Then GUI tells the UI manager that particular command comes, that's a string. Then UI manager interprets the string and identify who is the corresponding messenger and let that messenger deliver the message to the target class. Okay? For example, the typical case is, I believe you have already examined RAM bmon. Okay? There is a messenger that is named G4 RAM messenger. Okay? That takes the control of the run/bmon command, and it is registered to the UI manager. So once you type it, okay, the UI manager recognizes its messenger of the run manager to take care of this message. So it delivers how many events you want to proceed, that number to the run manager. So in this case, target is the run manager. In other case, you might have already changed particle kinetic, particle type. You switched from proton to pion or whatever. In that case, target class is obviously the particle gun. So basically, each target class should have his own messenger. Okay? And messenger can take arbitrary number of messages, or that means different kinds of commands. Got it? So messenger class. We have G4UI messenger base class. And messenger class, as I said, can handle more than one UI command. Okay? And messenger class should be instantiated by the constructor of the target class. So for example here. Okay? So when particle gun itself is instantiated, constructor of particle gun actually instantiate the particle gun messenger. Okay? And when particle gun itself object is deleted, of course, this messenger has to be deleted. Otherwise, your message will be lost. Okay? So messenger class has two methods in addition to the constructor and destructor. In the constructor of the messenger class, you have to define, that means instantiate command and on command directories. Okay? So let me come back to here again. So messenger owns whatever the number of commands. So these green boxes must be instantiated by you. That means by messenger. And messenger class is blue. That is that you have to implement if you want to have a messenger. Okay? Then destructor of the messenger. When messenger is destructed, you have to delete all the commands. Okay? Once command is deleted, this command disappears, so that even if a user types in that command, UI manager said there is no such a command. So that command will be refused, so it's safe. Okay? Then the third one, this is the first method actually you have to implement. Set new value. Okay? In this case, this method is invoked when actually UI manager realizes this particular command is actually typed in. Okay? So it comes with a pointer to that command itself and the string. String is all the values or parameters, but it still comes in as a string. Okay? And the last one, get current value, is, as I said, if you type question mark just in front of the command, you get the echo back of what the current value. Okay? So this method is actually invoked to get the value. So you have to return the string. That should be displayed on your terminal. Okay? So I believe you have already tried several different UI commands, so that you have already got a kind of image how things are going. Okay? Now to define a basic command. For example, although it said A01, it's quite a traditional name of what we are doing, our hands-on. Okay? It now has slightly different class name, but still detector constructor messenger. We do have it in our code, and in particular today's hands-on. Actually, it already had yesterday, so you can change the rotation angle of the second lever arm, right? Yesterday. So this is a command. So you really see in your hands-on code. So first of all, we create a new command directory, my detector. Okay, and add guidance. Okay. Then create a new command that is UI command with a double and its unit. So my detector arm angle. Okay. So this particular command of my detector arm angle should take two parameters. One is the actual angle, and its unit could be a degree or a radian. Okay. And then guidance, then parameter name, and range. That is this says the angle should be greater or equal to 0, and maximum value is 180. Okay. That means if user types the angle to -10 or 190, UI manager said, no, you cannot, because you have already defined the range. And the current value and the default unit here. Okay. So please note that the guidance could be more than one line. But the first line is used separately. That if you just type, for example, ls in the terminal, it restarts all the commands available with the command name and the first line of this guidance. So first line should be the minimum information or title, let's say, while all other lines of the guidance are for the details. So that once I use the type help with that command, all the guidance appears. And also, as I have already said, that once you type control/create HTML, UI Manager will dump all the HTML files for the guidance or guidebook. In this case, all of these guidance will be printed out, in addition to the range or default value and so on and so forth. That when you use, for example, the Qt window, you see on your left, if you pick the command, it says all the guidance and the default value and so on and so forth. Okay, all are kept in this way. Okay. So UI command is a class which represents the UI command. This is a base class. You can use the base class as is, and I'll come back to this later. But also, for your convenience, we have few more kinds of UI commands. UI command without parameter, UI command that takes string, UI command that takes a Boolean value, takes an integer, double, 3 vector, and directory. Please note, directory is also a sort of command which does nothing. Okay? And for the case of floating values like double or 3 vector, we may also use UI command with a double and unit or 3 vector and unit. Okay? In this case, the command also takes unit. And there are several methods for each of them. The first is a parameter name. That first method is available for the command that takes just one value. But second one is available only for 3 vector, so that it has 3 parameter names. Okay? And for this case, please distinguish each other. Use different names, say X, Y, Z, or PQR, or IJK. Okay? Should not be XXX. Okay? X1, X2, X3 is okay. And then the second parameter is omittable. If you say this yes, true, then the user can omit the value. And once the parameter is omitted, here, if you say this as a true, the current value is used as the default value. If you say this no, false, then you have to specify hard-coded default value. Okay? So in my previous example here, it said angle true, but the third argument is false by default. So that I have to set the default value here. Okay? So as you can imagine, depending upon how you say yes or true or false here, the behavior of the command is different. If the user omit the parameter, and if you say false, then the current value is used. Okay? While if you say true, then whatever the current value is, if user omit the parameter, it always takes the default value, fixed value. Okay? Okay, the next is range, set range. This is available for the command that takes numeric type parameters, integer or double. Okay? Sorry. And here, you can really type C++ kind of syntax. That's the reason why we definitely need here the different names. Okay? And if you say this the X, Y, and Z, that means you can use here X, Y, and Z. Okay? And in addition to the simple comparison, we also have some simple mathematics. Okay? So, this said, this command takes 3 vector values, and x has to be greater than 0, and y has to be greater than z, and z has to be smaller than x plus y. Okay? So it's really a powerful parser we have. So you can say this kind of range. Okay? So names of variables must be defined by the set parameter name method. This one. Okay? Then set default unit. This is available for the command which takes unit, so double or 3 vector. The once default unit is defined, no other unit of different dimension will be accepted. This is quite important to avoid any misuse of the command. If you say the default unit is centimeter, whatever the unit of length, meter, millimeter, micron, or feet, inch, is accepted. But by mistake, if you just say GeV, it's rejected because it's different dimension. It's a quite good way to avoid the misuse. Okay, so whenever you define a command that takes unit, please set default unit. Okay? And as an alternative, you can set the unit category rather than unit itself. That you say, this is the length. You can also do that, but almost always it's better to just define the default unit. Okay? It's quite good way to avoid the misuse. Okay? The set candidate is for the string type parameters. For example, for the case of Geant/particle command, actually we use this. First of all, we access to the particle table and get the name of all the particle registered and create a big string. And use double quotes and set this. Okay? So when you have more than one candidate, use a pair of double quotes to make a string. Okay? Now, available for states. Geant4 has several different application states. Geant4 is a state machine. So it program always starts with play init. And once you invoke run/initialize or invoke the method of run manager initialize, it comes to the initialization state. Okay? And once initialization is done, it comes to the idle state. Okay? This init state may not be quite visible to you because it turns into init when Geant4 starts to initialize itself, and once initialization is done and come back to you, it's already done, so it comes to the idle. Okay? So idle is a state where geometry is already built, all the physics models have already been instantiated, so that you are ready to go. Okay? So once you type bmon, then it comes to geometry closed, and once geometry closed means we calculate cross-section table depending upon the cuts and material you specified. And we optimize the geometry. And once we are ready, we make one event processed. And as soon as one event is processed, it comes back to geom closed. And then basically it toggles between these two until the time all the event is done. And once all the event is done, it comes back to the idle. Okay? And so during the event loop, application is either in the geom closed or event processing. Okay? And once you type exit, it's done. It comes to the quit. And if something unpredicted happens, something goes wrong, it goes to the abort. Okay? So you may define your command available or should be available only for the particular state. For example, if you want to change the geometry, that command should go to your detector construction, yes. But we cannot change geometry while we are in the event loop. Okay? So basically, you have to say, if you have create a UI command that should change the geometry, the command should be available only for the play init and idle. Okay? Yeah, init is also okay, but should not be in a jump close or event processing. Okay? So now you got the usage. Okay? So just say, please don't take this command when Geant4 is that particular state, or accept only if this Geant4 is in that particular state. Okay? Okay. Now, once you successfully create a command, and you now your program is actually running, then once a user types in a command, he or she types a command with parameters, but parameters are character string. So once user types in a command, this set new value is invoked. It comes a pointer and string new value. Okay? And if a parameter is omitted, UI manager has already taken care of filling it with the default value. Okay? So you don't need to worry about omitting if you use the base class or any of these ones. Okay? So we have get new Boolean value. So you just put string here and get the bool value and so on and so forth. For the case of double and 3 vector, you get double and 3 vector. Okay? And unit is already taken into account automatically. So if your command should take the length, whatever the value of the length, and so the command should take value and unit. If you say the user said 1 kilometer, once you use this method, you already get the value which is already multiplied 1 times kilometer. So it's already in the Geant4 internal unit, which you don't need to know. Okay? So just use it and set it to a geometry. Okay? It's convenient. And just for the sake of the question mark, that put in front of the UI command so that the user want to know what is the current value. There's a method to convert whatever the value to the string. So you return it. Okay? So this is an example of the famous arm angle. So given a messenger may take more than one, messenger may handle more than one UI commands, you have to first of all examine what command is actually invoked. So check it if it is arm command, and if it is the case, okay. First of all, you convert it to a double, and set to the detector construction. That's it. You are done. Okay. And if question mark is typed, and if command is an arm command, first of all ask to the detector construction what is the current value. Okay. And multiply the unit in this case, and convert it to string, and string has to be returned. Okay, that's it. Okay, and I invite you to actually look at your hands-on code. That is quite informative. Okay, and now let me proceed to a bit more complicated UI command. We already have these quite handy commands, but time to time your command need to take more complicated parameters. Okay? In this case, you can directly use the base class, G4 UI command. And G4 UI command base class can take arbitrary number of the UI parameter object. Each parameter object is just one parameter. Okay? And it takes name, type, and omittable. Okay? And type could be Boolean, integer, double, or string. Okay? Each parameter can take one line of guidance. Okay? And you can set default value in case the omittable is set to true here. Okay. Okay, so given a UI command object can take arbitrary number of parameters, names of the parameter must be different to each other within that command. Suppose you are creating exactly the same command by this base class for the 3 vector, then it has to be x, y, and z. Rather, should not be x, x, x. Okay. So gun ion command is a good example. This is a command of particle gun where you specify what kind of ion rather than elementary particle you want to shoot. Okay. In this case, basically that's the command that shoot that define atomic number, atomic mass, charge, and excitation energy if you want. Okay. So it takes 4 parameters. 3 of them are integer, and the last one is double. And I'm a bit lazy, so that in this case, you cannot change the unit. Okay. Anyway, so in this case, you just one by one instantiate a parameter, one after the other, and set it to the command. In this case, the order matters. The first parameter, it should be set to the command first. Okay. So the first one is the parameter name is z. It's integer, and you cannot omit. The second parameter is a, atomic mass. It's integer again. You cannot omit. The third is q. It's integer, but you can omit, and so that default value is 0. Okay. Then the last one is e, excitation energy. It's a double. It's omittable, and default value is 0. Okay, that's it. So that this command can take 4 parameters. And when the set new value comes, in this case, you really have to take care of omitted parameters as well. And we do have tokenizer. Tokenizer is, once you got the string, it's tokenized. It makes strip to each individual value. So the first one, whenever you invoke next, you get a token. Okay. So the first one has to be atomic number. So just convert string to integer and so on and so forth. Then the third one, given it is omittable, you have to check if it is omitted. If it is null, that means it is omitted. So take whatever the default value. If it is not omitted, you get the value, so convert it. Then go to the next. If it is omitted, and so on and so forth, you continue. Okay. So once you have a base class UI command with base class parameters, you have to implement this. For the case of simplified commands, this is already taken care. Okay. So for your convenience, we have these converters. So be careful of omittable parameters. And if you don't like to worry about this, make all parameter not omittable. Okay, that's the simple way. Any question? So I do invite you to look at, where is it? This command. That is in the, if you go to the LXR code browser, get into the event category, and you should see particle gun messenger. That because particle gun takes a lot of different ways of the parameters in a lot of different ways. So it's really useful as an example. Okay. Now, general messenger. It's a shortcut. You have to be very good for C or C++. Okay. It's handy, but you really have to understand what you are doing. For example, it takes, time to time, it takes a pointer of a method rather than variable. So it's really complicated. So if you are confident just come back to this. This actually allow you to not create any messenger class, but in your target class, you can directly define a command one by one. Okay? So you have to understand what any type means and kind of things. I don't quite understand well yet. Okay. It's really by C programming experts only. But we still have some example because the usage is very handy. You don't have to have messenger. Just construct a generic messenger, momentum command, and so just follow these recipes. Basically, the parameter name, range, def, and kind of things, it's the same. Okay. Okay. To finish up, just one comment about your multi-threaded mode. In multi-threaded mode, each thread, both master and worker, has its own UI manager object. Okay? So command instantiated in a thread are registered to the UI manager of that thread. That means if a particular class is instantiated only in the worker thread, okay, that exists only in the worker thread. So, every UI command is executed in the master thread, first of all, because only the master thread has a direct communication with your terminal. Okay? So once the user types in a command, it always comes to the master thread. Okay? Then it is broadcasted to all the worker threads. Okay? UI manager of the master will take care of this broadcasting. But time to time, you don't want this broadcast to happen. Because in some cases, you really want this command to be applied only to the master. If this is the case here, you can set to each individual command, set to be broadcasted false. That means if you say no, it will not be broadcasted. Okay? And please be careful, one thing, that UI command can be executed not by typing in the command, but hard-coded way that we have already discussed. But if this happens in a worker thread, this will not propagate to the other worker. This will not propagate to the master. It happens only in this particular worker. Okay? That is something you have to remember. That is also another reason I recommend not to use hard-coded UI command for the classes that goes to the worker thread. Okay? Got it? Okay. So, did I run too much or I'm short? I don't remember.
Originally, it was supposed to finish at 10:30.
Okay. Okay, so shall we start 20 minutes from now? Or if the coffee breaks are ready? Or we start the session, next session now? Okay. Okay, let's get break for 20 minutes.